Okay, let us continue the second part of today's course. This chapter derives the MIMO capacity formula based on Taylor's arguments. The expression we develop in this chapter will be used to quantify the throughput enhancement. Okay, we have taught you what is the throughput. If you forget, please review the handout of chapter 1. Okay, throughput enhancement that is possible with spatial multiplexing, as well as to provide a useful way of conceptualizing how MIMO systems work. Okay, here is a footnote. Let us see. Footnote 1. As stated in the preface, this book does not assume the reader has had a formal course in information theory. Thus, basic concepts from information theory are introduced in this chapter. The reader who is already grounded in information theory should feel free to skim through the first few sections of this chapter. Readers desiring additional background are referred to reference 18. Okay, reference 18 is a very famous textbook, or you can call it the Bible of the information theory, which is written by Thomas M. Carver and Joy A. Thomas. Elements of Information Theory, 2nd edition. Wiley Series in Telecommunications and Signal Processing, Wiley InterScience 2006. Okay, then let us go to section 2.1. What is information? Okay, in its most fundamental sense, the capacity of a communication system is defined as the maximum amount of information that can be conveyed per unit of time between 2 points over a communications channel. In order to have a definition for capacity that is useful for engineering purposes, it is necessary to be able to quantify it, to be able to assign numerical values to the capacity of a communication system. This section introduces you to the formal definition of information as it is used in information theory. An interesting aspect of information theory is that it is based on the use of the word information as used in everyday speech. That is, the way we use the word information in everyday conversation helps motivate the way information is defined mathematically in information theory. To help see this, consider the following two statements. Statement 1. It snowed in Anchorage, Alaska this morning. Statement 2. It snowed in San Juan, Puerto Rico this morning. We first ask which statement intuitively conveys more information, assuming, of course, both are true. Let me give you a hint. In Anchorage, it is a very cold city. And in Shenwan, it is a very hot city. So what is your opinion? Okay. Most people would say that statement 2 conveys more information because snow in San Juan, Puerto Rico is unheard of, but snow in Anchorage, Alaska is a very common event. Instinctively. Okay, what is instinctively? Let us see the handout. Okay, sorry. Okay, page 13, problem 1. What is instinctively? Solution: instinctively is an adverb. Instinctive is an adjective. Definition of instinctive. 1. Of relating to or being instinct. 2. Prompted by natural instinct or propensity, arises spontaneously. For example, an instinctive fear of innovation by V. L. Parrington. Okay, let us go back to the slides. Okay, instinctively we sense that we have learned more when we are told about an inherently. Okay, what is inherently? Let us see the handout. Okay, problem 2. What is inherently? Solution: inherently is an adverb. Inherent is an adjective. Definition of inherent. Involved in the constitution or essential character of something. Belonging by nature or habit. Intrinsic. For example, risks inherent in the venture. Okay, let us go back to the slides. Okay, inherently improbable. Okay, the word improbable, I think you may know. It means impossible. Event. Then when we learn about something that is commonplace. Okay, what is commonplace? Let us see the handout. Okay, problem 3. What is commonplace? Solution: commonplace is an adjective. Definition of commonplace, entry 1 of 2. Commonly found or seen, ordinary, unremarkable. For example, a commonplace occurrence. Another example, the large mergers that had become commonplace. And another example again, computers are commonplace in classrooms. Commonplace is also a noun. Definition of commonplace, entry 2 of 2. 1a. An obvious or tried comment, truism. For example, it is a commonplace that a fool and his money are soon parted. B. Something commonly found. A smartphone is a commonplace. Okay, for example. 2. Archaic. A striking passage entered in a commonplace book. Okay, let us go back to the slides. This is one key property of information. The second key property of information can be grasped by considering the following statement. Statement 3. It snowed in Anchorage, Alaska, and it snowed in San Juan, Puerto Rico this morning. We now ask how much information is conveyed by Statement 3 compared to the information conveyed by Statements 1 and 2 separately. Okay, what is your answer? Okay, let us see. Instinctively, we would say that the amount of information in Statement 3 is equal to the amount of information in Statement 1 plus the amount of information in Statement 2, since Statement 3 includes everything in Statements 1 and 2. From these simple observations, we can deduce. Okay, what is deduce? Let us see the handout. Okay, page 16, problem 1. What is deduce? Solution. Deduce is a verb. Deduced or deducing. Definition of deduce. Transitive verb. 1. To determine by reasoning or deduction. For example, deduce the age of ancient artifacts. Another example, she deduced from the first dog to his clothes that he owned a cat. Specifically, philosophy. To infer, see infer sense 1 from a general principle. 2. To trace the course of, for example, deduce their lineage. Okay, let us go back to the slides. Deduce that information as it is commonly termed in everyday language as the following two properties. Properties of information deduced from everyday speech. Property 1. Statements about inherently improbable events convey more information than statements about inherently likely events. Property 2. Information is additive. Based on these two properties, it is possible to develop a mathematical definition of information. Consider an event that has an a priori probability of occurring, P. If we are told that such an event has indeed happened, then the amount of information, capital I, that is conveyed by learning of what that event's occurrence is defined as follows. I of P is equal to log of 1 over P is equal to minus log P. Okay, you may ask a question. Is it the log 2 or log 10 or log E? E is the base of the natural logarithm. Okay, you do not worry about it right now. We will answer you this question later. By inspection, we see that equation 2.1. Okay, equation 2.1 is this equation. Satisfies property 1. Since log 1 over P increases as P decreases. Property 2 follows from the property of logarithms. To see this, consider two events with a priori probabilities of occurrence equal to P1 and P2. Assume furthermore that these two events occur independently of each other. That is, the occurrence of one of the events does not affect the likelihood that the other event will happen. Under that assumption, the probability that both events occur, P12, is equal to P1 times P2. If we learn that both events have occurred, then by equation 2.1, equation 2.1 is this equation. The amount of information that is conveyed is given by I of P12 is equal to log 1 over P12 is equal to log 1 over P1 times P2 is equal to log 1 over P1 plus log 1 over P2. This is from the property of the logarithm. I think you have learned it when you are in a senior high school. And according to the definition of information, it is equal to I of P1 plus I of P2, which demonstrates the desired additive property. Because I of P12 is equal to I of P1 plus I of P2. The definition of information in equation 2.1. Let us go back to 2.1. This equation, I of P is equal to log 1 over P is equal to minus log P. The definition of information in equation 2.1 is general in the sense that it does not specify the base of the logarithm. There are an infinite number of possible bases. However, only base 2 and base e are used in practice. E is the base of the natural logarithm. Is equal to 2.7128, 7128, etc. When the base 2 logarithm is used, the units of information are bits. Bits is a compound of two English words, that is, binary digits. When the base is e, the units of information are referred to as nets. Nets is also a combination of two English words, that is, natural digits. In the derivation of MIMO capacity in this chapter, we occasionally alternate between these two bases, depending on mathematical expediency. Next, let us go to section 2.2, entropy. In the previous section, we introduced the mathematical definition of information associated with random events. Since random events in turn are characterized in terms of random variables, it is reasonable to associate information with random variables. This slight abstraction enables us to analyze the information properties of random systems using well-defined properties from probability theory. Consider a discrete random variable, capital X, that can take on values small x1, small x2, etc. Each time capital X takes on a specific value, the instantiation of capital X is an event. In general, we can speak of the information associated with the event. Capital X is equal to small xi, I is equal to 1, 2, and denote that information by I of small xi. Using equation 2.1, okay, let us go to equation 2.1. Okay, I of p is equal to log 1 over p is equal to minus log p. Okay, it follows that the information associated with capital X taking on the value small xi is given by I of xi is equal to minus log p of xi, where p of xi is defined as the probability of capital X being equal to small xi. Now that we have information defined in terms of a random variable, it is natural to consider the average information associated with a given random variable. In information theory, we call the average information the entropy, which we denote by h of x as follows. Okay, entropy is equal to h of x and is defined as the expectation of I of x with respect to x, and is equal to the expectation of minus log p of x with respect to x, and is equal to minus summation I. Okay, because here is a minus, we can move the minus out of the summation, and p capital X of small xi times log p capital X of small xi, where p capital X of small xi is the PMF, that is the probability mass function of the random variable capital X. The entropy of a random variable also has the following interpretation. It is a measure of the uncertainty in our knowledge of the value of that random variable. So in Chinese, we can translate entropy as 乱度. To see why that is true, consider the extreme case where a random variable capital X has no uncertainty. In that case, capital X is equal to small x0 is the value of the random variable, and its distribution function is equal to 1 at capital X being equal to small x0 and 0 at all other values of capital X. Apply this to equation 2.6. Okay, let us go back to equation 2.6. Okay, equation 2.6, entropy is finally equal to minus summation I px of xi times log px of xi. Okay, results in h of x, that is the entropy, is equal to minus px of x0 times log px of x0 is equal to minus 1. Okay, because this term is equal to 1 times log 1. Okay, because this probability is equal to 1, and it is equal to 0, which is, okay, it is 25 minutes. Let us take a break.